Right. So good evening, everyone, and welcome to tonight's lecture. So it gives me great pleasure to introduce tonight's speaker, Richard Cook from Casting Technology International, who's going to tell us a fascinating history about the organisation and where it's going for the future. So thank you very much for coming tonight, Richard. Over to you.
Thank you. Good evening, everybody. And I'd just like to say to the organisation, thank you very much for the invitation. So, been asked to talk about Castings Technology International, a company that has a rich heritage, sort of past, present, and future. We'll look at the past history, some more recent history, and then ultimately what we're doing at the moment, what we hope to be doing in the future. And I'll try and weave into that a little bit of discussion around the MBO process that took place in January of this year. So, after both world wars, the government had a desire to promote and support the casting industry. After the First World War, cast iron in particular was a growing commodity, and the BCIRA was formed in 1923. And then subsequently after World War II, where steel was becoming much more prevalent, the Steel Casting and Research and Trade Association was formed, otherwise known as SCRATA. And then that was in 1953. And then those two organisations ultimately merged together to form what became Castings Technology International. In 2006, the majority of CTI, as I'll use the acronym, moved to the Advanced Manufacturing Park at Catcliffe. For those of you who aren't local, I suspect most of you are, that's near Morrison's, just off the Sheffield Parkway, which is how it tends to get routed in the absence of sat-nav. So when I say the majority of the operations, there was a subsequent move, which I'll come to in a second. But in August of 2013, the AMRC, or Advanced Manufacturing Research Centre, was pursuing three particular threads of manufacturing. And their expertise was in subtractive manufacturing, so what we would call machining as engineers. And I'll come clean now and say all of my background is machining. So if the metallurgists would go really easy on me tonight, I'd be grateful. And I only really got to explore the world of castings from about 2014 when I joined the business. So in 2013, July, August time, the University of Sheffield bought the CTI, and they did that because the next natural progression from subtractive processes like machining is to get near net shape, particularly when it comes to aircraft structural parts, where you might start with a block of aluminium of significant weight and turn 90% of it into swarf to create a matrix for a wing or fuselage section. And they got very, very good at the machining side. ALM is on the horizon. Obviously, everybody's talking about 3D printing, particularly of metal parts. But as I'll cover in the presentation, we don't believe that's quite there yet. So in the middle there is this near net shape. So making an acquisition of Castings Technology International made strategic sense for the Advanced Manufacturing Research Centre, which of course is wholly owned subsidiary of the University of Sheffield. So I joined the business shortly afterwards in the January of 2014. And in 2017, we brought the remainder of the business up from East Bank Road, or the old Replicas facility, as many local people will know. And then after numerous business reviews, the university arrived at a decision to carry out an orderly wind down of the business, resulting in closure in December of last year. And I was, as you can imagine, a little bit upset about that for a whole host of reasons, which we'll cover in the presentation. And after an awful lot of negotiation, something like 6 months worth, in January of 2021, myself and Kevin Parkin, some of you may know Kevin, he's a local industrialist who's done a number of business turnarounds, managed to get an MBO over the line, despite the best efforts of others, shall we say. So at this stage, I always like to pause and reflect on us moving up to the Advanced Manufacturing Park and what that really means to the local region. As a regular visitor to the Sheffield area as a youngster, even though I'm a Midlander, more specifically God's County of Leicestershire, it always amazes me of what the landscape looked like around Orgreave and Catcliffe at that period in time. And this is just after the coking plant had closed and become slightly derelict. And then in contrast with that, just sort of a few short decades later, and this is an artist's impression back in 2018, and nearly all of this, by the way, has happened in that time scale. You'll see our two buildings just beside the very large windmill there. I'm sure there's a pointer on it, but I'll use my finger. So that's our number 1 building, and that's our number 2 building. It's not recent enough to have McLaren on there, which is just around the corner, and some great names, including Rolls-Royce and so on. And just across the other side of the parkway, of course, we attracted Boeing's only manufacturing facility outside of North America as well. So the transformation that was created by the Advanced Manufacturing Research Park is tremendous. And it's great to be on there, I have to say. So what about CTI? Well, I'm just going to give you a brief overview, then I'm going to hone down into some of the processes. So we have around 80 highly qualified engineers, and they range from very skilled operators through to people doing administrative support tasks and engineering in the background. And we have, for a relatively small business, a very large global footprint. So we have a licensee who has exclusivity in China. We have a licensee who has exclusivity in India. We also have members throughout the world. And at the moment, as it mentions there, we're partnering with about 115 members. So we still retain that members feel to the organization, even though commercially we've branched out from that. And the reason I put up the graphic there about MRL, TRL, a popular Department of Defense rationalization of manufacturing processes, what set us apart within the AMRC when we were still part of the university is that they focus very heavily in 1 to 6. So getting to sort of pre-production is where their expertise is. However, CTI go throughout the entire range from 1 to 9. So we can do blue sky, R&D, development of new alloys and so on, all the way through to going into established processes in large foundries and looking at optimizing the process further. So we do a broad range of services. In terms of what we do in the building, plant and equipment, I'm not going to go through this line by line because you're quite capable of reading it off the slide. But I think the important thing is still traditional pattern making skills. So we have guys every day that are making patterns using wood, foam, generally low melting point materials for the patterns, but then an awful lot of wood for the feeding gating systems and so on. So the materials obviously selected to suit the most appropriate ones for the process. We're going to focus this presentation around ceramic shell casting. So ceramic shell manufacture, probably one of our most critical processes. Heat treatment furnaces, melting furnaces. So we have the whole gambit. We have quite a high level of vertical integration, so we don't have to subcontract too much work out. The exceptions being chemical milling, which is a pretty unpleasant process that we don't really want on site, involving neat hydrofluoric acid, and also hipping or hot isostatic pressing, which the capital requirements for are huge, and we don't have the space for a hip vessel, unfortunately. But as you can see down there, we've got a whole host of both traditional foundry practices and also some less traditional ones. Some great approvals. We have a full ISO and AS 9100 accreditation. On key processes, we also have NADCAP approval, and our lab is UCAS accredited. And I think quite important is to sort of take in that last line, which is between the university taking ownership of CTI in August of 13 and the MBO, there was an investment of around £30 million of public money into the business, into the facilities and equipment, and some of that you'll see in photographic form on the presentation. So some of our activities, and we'll come back to the breadth of what we offer. We do make castings. We quite like making castings, and we like to think we're quite good at it, but we don't limit ourselves. We're not precious about casting because there are other services we can offer that are they're good for UK PLC in particular, but also for overseas advancement of casting technologies. So we offer consultancy, we offer design for casting manufacture support. There's a whole host of other things that we offer in addition to series production of castings. And you'll pick up there on the machining side, we machine a lot of foam because we use foam as a pattern material, a low melting point material. We also machine sand, so we can print sand 3D. We can also ram sand in the traditional sense and then machine shapes into it. we machine ceramics, wood and metals as well, including some proof and finish machining of castings. And as I mentioned, all the way through the gambit from carrying out research and development. The important thing for us as a business, when it comes to research and development, is we can exploit it. So it's not just about doing some research and development. It sits as a paper somewhere, all very nice. What we can do is we can take it to market as well. And it's one of the key reasons we stayed with the AMRC for so long. So these things tend to set us apart. I've already mentioned the breadth of offering. We also have 3 primary casting processes within the facilities. One, investment, and the reason I put an asterisk by investment is, for the purists, we don't do investment casting, because investment casting goes into a hot ceramic shell, and everything we do pretty much goes into a cold ceramic shell. And when I say cold shell, usually the next question I get is, you don't really mean cold, do you? You have a heater on, it'll be a few hundred degrees. No, we mean room temperature cold, and that it goes for titanium as well as the other metals that we melt. We have, unusually for a foundry, we cover a whole wide range of materials. We're the UK's only titanium foundry, but we also melt aluminium. We do all the steels through stainless to super duplex. We occasionally do iron. One of the few materials we don't do is magnesium. We subcontract magnesium out. But it's, as I say, whether it's light alloys, nickel-based alloys, titanium, we cover a wide range of materials. We have, and we're very proud of this, we have a combined experience base which stretches to hundreds of years. And if that sounds a little bit like a porky pie that I'm telling there, we've got 2 members of staff with 40 years service, which gets us quite close to 100 years with just 2 of the 80. And we have a lot of long servers, and that's great because that experience stays within the business and grows. And it's one of the reasons we get such a lot of interest from consultancy support, because our guys that go out and consult have seen it all in every part of the world, good, bad, and indifferent. So, and you might think the last bullet point is a bit of an odd thing to say. So we have a culture that we're quite easy to work with. Strangely, in the foundry sector, being easy to work with is not a primary concern of a lot of the foundries I've come into contact with, and certainly not when it comes to high-end titanium, which is generally controlled by 2 or 3 North American companies. So we set ourselves apart to be very, very easy to work with. So I'm just going to put this example part up because the next phase of the presentation walks you through the process we use to create an investment cast suction impeller, which is what that is on the screen. The reason I put that picture up is A, to create a vision in your mind, but also to look at the quality. That's as cast. It's not a machined part. That is as it's come out of the casting process. It will have been inspected and weld upgraded if necessary, but there's no machining on that part yet. It's come out of the shell and it's been grit blasted, heavily grit blasted. And as you can see, our process, because it uses generally a single pattern, so in a normal traditional pattern process, you'll know that you have a wooden pattern, ram sand, you press that shape in, you'll probably have a core box and you'll be fitting numerous parts in. And with every one of those parts, there's an accumulation of tolerance and so on. We don't have any of that. We print the pattern, usually in 3D, or machine it in foam, and it's a single piece. And why that's important, we'll come back to a bit later on, but what I would like us to think about is it's not just the accuracy of that part in terms of tolerancing, it's the geometrical relationship between those veins is consistent, very accurate, and the blade form's very good. So it wouldn't be the first time that people have bought impellers using old empirical data that have broken the pump casing because it's over pressurizing the pump case. It really does change the hydrodynamic performance of rotating parts. So this is the part that we're going to run through in terms of some of the things we do. That's what they look like when they've been finished, machined. So as you can see, a lot of these parts that you saw on the other picture, looking around the periphery, are as cast. It's just the outer surfaces where it has to mate with other parts that are machined. So we utilize 3D solid modeling, as a lot of companies do nowadays. We don't generally get involved in physically designing a product from scratch. What we do often get involved with is consultancy on design for casting manufacture. Because of castings, the legacy, there's probably a whole generation of engineers come through and been told that casting's a bit suboptimal as a process, which is slightly unfair, particularly given the advances. But there's still a tendency to design with machining or fabrication mindset. And what we do need sometimes to discuss with the design authority is what sort of corner radii. If we can increase the corner radii, we reduce the opportunity for a crack, and so on and so forth. Very basic stuff, offsetting web so that we don't create an isolation in the design. So, and using 3D modeling for that is a real bonus. I would say 90% of what we do these days comes to us first as an inquiry with a 3D model. Then what we do, we often make one-offs in small quantities. Now, I don't know about any of you guys, but I did my apprenticeship being told that, you know, unless you've got 1,000 to make, don't even consider casting as a process. But we do an awful lot of one-offs. Our average batch size will be around 2 or 3. And even where we do volume, we've got a contract on F-35, the Joint Strike Fighter at the moment, and we're making 40 parts a month for that, but there are 9 part numbers, so it's still relatively low volume for each individual component. But what we do have to do when we have so few parts to go at is to do as much upfront simulation in the digital world as we can. So all of the castings we make have a full process simulation carried out, sometimes prior to quotation. It really depends on the type of part. And we'll almost always run a fill and solidification simulation as well. And it's surprisingly accurate. We wish that we could go one step further and model the shell as well for its dilation and propensity to crack, but unfortunately that technology doesn't exist at the moment. Then what we're going to do, depending on the geometry of the part, so this very much suits the photograph that I put up at the beginning, we're going to make a pattern or a replica, hence Replicas, of the part that we want to make. And that's very traditional in investment casting. But what we do need, we need a good low melting point material that's going to give us a reasonable surface finish. So foam tends to be entry level. We machine foam. Some of the limitations of foam are surface finish, although we can wax the outside to help with that. But also, remember, we're machining foam, so we can only make shapes that you can machine on a multi-axis machining center. Whereas with SLA, we're building these patterns in layers, and these are known as quick cast patterns. And if you don't know, one, it's Yorkshire, the resin's expensive, so we don't like to use very much of it. But joking apart, what happens is if we create this in a solid resin, put it in a ceramic shell, and then try and fire it to burn it out in an oven, the first thing it will do is expand, and that cracks the shell. So what we actually create here, although it looks solid, inside is a honeycomb pattern. That reduces the amount of resin that we use. It also, when that's exposed to 1,000 Celsius, it tends to crumple in on itself. There's lots and lots of trapped oxygen, and it helps to burn it out. We don't want any ash or waste left in there. And that allows us to create a real good replica of the part with a little bit of contraction allowance on it. So that is our go-to process for low volume, high integrity Class A impellers. It's a very expensive process, by the way, but very, very good at what it does. Having done that, we're going to put that in a cage, whether it's SLA, foam or wax, whatever the low melting point replica is made of, they are quite fragile. Then we're going to add ceramic to it, which is not known for its robustness and toughness. So we put everything into a standard cage. We have a range of standard cage sizes, and we're going to create that ceramic shell. And that's made up of a number of layers of alternating between wet ceramic slurry and dry granulate ceramic. And in between each of those coats, there is a drying cycle. Not firing anything, it's literally about 25 Celsius, a warm, low humidity environment. Because what we do want to do is we don't want any wetting back. Yeah, you put a wet coat onto some plaster or ceramic and it's likely to soak in. We want to draw the water out. So that's relatively low temperature. And that might be up to 30 coats. It all depends on the material type and the geometry. And that leaves us eventually with a ceramic shell that looks a little like this. This is the best photograph I could get today because the only thing I was missing was the shell. And it's had a section cut out of it, but you get the general idea of the relative thickness of the ceramic, and balancing that, as I'll mention in a moment, is really, really important. The reason that's blue inside is that the prime coat, which is the first coat you put on the model, is the most important one. It's the most expensive. It's the one that's the KFC recipe that nobody gets to know about, because that's where all the technology is. That is the coat that's going to see the incoming metal stream, which is going to be significantly hotter and heavy. as it splashes into the shell. This particular one is blue because it has cobalt in it. Cobalt helps to promote nucleation on certain materials, but it gives you an idea of what a ceramic shell actually looks like. And then we're going to melt and pour. In this case, I picked on atmospheric melting because the part, as described, is super duplex. We melt that generally in atmosphere, depending on the specification. And we have a relatively modest melting capacity for steel. We have 3 furnaces, so we're able to make a range of parts without melting too much material, and they're on a single electrical track, so we can melt all 3 at the same time and create around about 3 tons of molten material. Now, because our yield using this process is relatively low, that will give us a finished casting of around a ton and a quarter, something like that. The rest of that material is part of the process. It gets cut off, it goes back into the process and gets recycled, of course, like most metals do, but the yield is relatively low on this process. And then you may well ask yourself, well, that ceramic shell is at room temperature. We're bringing steel into it probably around 1600, somewhere depending on the spec, 15 to 1600 Celsius. We're going to bring it down in a down screw. We're going to fill that ceramic shell quite quickly, 25, 30 seconds, with maybe up to 3 tons of molten metal, and you're going to elevate its temperature almost instantaneously to around 1600 Celsius. And it would be naive to expect the shell to survive that on its own. So outlined on this particular photo is the Replicas box down at the bottom here, and you'll see a number of vents and also the down screw. And what we do there is we put the shell in its entirety inside a steel box. We surround it with standard silica sand, nothing special about the sand. What is special about the process is we then put a sheet of plastic across the top. We connect the box to a liquid ring vacuum pump. And if you've never done this experiment, if you do that, you find that the sand solidifies. So missed out an operation which is vibrating the sand. So we keep settling it like you would with a salt pot. And when it's settled to a certain frequency and time, we then pull a vacuum through it. So we used to do it at exhibitions, actually, with a sword in the sand. People will come along, pull it out, put it in. If you pull a vacuum over the sand, you cannot get that sword out of the sand. So what does that do? Well, you can imagine at the grain of sand level, every small part of that ceramic shell is supported. And we keep that vacuum on until, well, for a relatively short period, because we don't want to suck air into the melt. So we leave it long enough until the ceramic has survived, then we switch off the vacuum and allow it to solidify and cool. And cooling takes quite a long time. Sometimes we hot strip it if the spec requires it, but generally it's left in there to cool, and it can take a couple of days for it to be able to be touched by hand. So that's the Replicas process that produces the main number of our impellers. And then, as most foundries have, we have a range of NDE equipment, including LPI, MPI, and X-ray. And again, you'll see that's a suction impeller there with some defects identified. Those defects might be the form of an inclusion or a crack, and that is, depending on the specification, that's assessed, and a repair is carried out, usually a grind out and a weld repair, and then it's retested to make sure that it meets specification. And what we should end up with is, something with a very fine surface finish, good geometrical relationship, which is really what we're after, much more than just accuracy, and that leads to that excellent hydrodynamic balance and pumping performance that I mentioned. Cavitation is a real problem on rotating equipment, and if you can avoid it, then you eliminate a lot of wear potential, but also noise in the process as well, and premature wear to upstream and downstream processes as well. And what tends to happen with our impellers, you can see just a snapshot here. This is a well-known UK pump OEM. I won't mention their name, but they're in Leeds, which probably gives it away. Double suction impeller diffuser and single suction impeller train. And if you've ever seen a very high performance pump, they tend to have lots of these in a long train, pumping all sorts of materials from, particularly sometimes some very difficult to process materials, which involve then coating the casting sometimes, or alternatively going up the material scale. So in some cases, they go to titanium for corrosion protection, other times nickel-based alloys for particular acids, and so on and so forth. So it just depends on the application. I mentioned titanium, so I'm going to talk about that in the investment cast sense, because most of the titanium casting we do is through the investment process. We all know titanium is a very versatile material, quite expensive, but it's generally been the preserve of aerospace. So certainly in the forces, we're involved quite heavily at the moment with the Navy and the Army, who want some titanium action, because Biggles has had it all these years and they want a bit. And I joke, but it might not surprise you, I'm sorry, it might surprise you if I said that the Ministry of Defence are estimated to spend £1 million a day alone on corrosion, the aftermath of corrosion, repairing or replacing parts that have corroded in service. So titanium is quite high on their agenda at the moment. I've mentioned previously, it's our only, we are the UK's only titanium foundry. And the thing about titanium is it's very inert, very strong, very light when it's solid. Like most materials, it doesn't like to be molten and wants to get back to its solid state as quickly as possible. The difference between titanium and other metals is, whilst it's in that state, it's highly, highly reactive. And that means we have to work very hard on the chemistry of our prime coat, the first coat that sees the metal as it comes in. But also we have to avoid oxygen getting anywhere near it at all costs, and particularly water, which we'll come to in a second. And bearing in mind, we're still using cold shell technology, and there's only one other foundry in the world that we're aware of that's cast titanium into a cold shell. And because titanium tends to freeze off quite quickly, if you need to get it into thinner cross sections, then you need to centrifugally spin it as well. So not only is the shell got to put up with a sudden ramp up in temperature and the mass of the molten metal, it's pulling 20 G at the same time, roughly. So the shell makeup is probably the most critical of the things that we do. In recent past, and ignoring the pandemic just for a moment, we've seen a bit of a perfect storm in titanium, in the sense that there's becoming a bit of a dearth in capacity. A very large North American foundry closed its doors 2.5 years ago now. And if you look at the build profile for Airbus and Boeing alone, it's frightening. It was getting to the stage of, I think, at its peak, 43,000 aircraft in the next 20 years. And if you work that back to a daily output rate, it really is quite frightening. You know, they're not building Land Rover Defenders, they're building aircraft at an alarmingly fast rate. That's about halved as a result of the pandemic. But nevertheless, the combination of a reduction in global capacity with a corresponding increase in build of aircraft, and we are in a position, hopefully, to exploit that as flight numbers increase in the future. And the picture there, we suspect is the largest ceramic cast titanium casting in the world. That required a melt of over a ton of titanium, and there aren't so many people in the world who can create that. And it's why, as I'll come back to, the MBO was so important to us. And you'll also see, by the way, and I'm very proud, I'd like to mention this, we won an Athena Award at the turn of the year for our diversity in our workforce. We have, I suspect, Europe's only female methoding engineer. We also have a number of female staff working in titanium upgrade, which is for, well, decades been the preserve of male staff. But because we make a lot of smaller titanium castings, dexterity really does come into play. And we have about a 50% contingent of female staff in our finishing section for titanium. Titanium's a distinctly different process. So up to this stage, if we were going to make that impeller that I've showed you so far in titanium, all of the process up to this point would have been identical. So make a pattern, make a ceramic shell, burn it out, and so on. But with titanium, as I mentioned, it's very reactive. So we're going to carry out the melting process under a very, very high vacuum. And that's the case with everything we do with titanium. If we have to weld it or anything, it's all done under vacuum. We have a significant temperature delta between the crucible we're melting the titanium in, which is made out of copper, and the titanium itself. And as you can see there, it's a differential of some 650 odd degrees or just under. So we have a lot of water cooling, and which runs constantly around the copper crucible, goes outside to heat exchangers and comes back in the building. And all the while we're centrifugally spinning with some fairly fragile shells, which could weigh several hundred kilograms each, spinning at 20 G. So there's a lot going on in there when we're melting titanium. And what we need to avoid at all costs is any water getting the wrong side of the copper. Because if that happens, you're elevating that water, which is probably at 4 or 5 degrees Celsius, to 1735 instantaneously, which creates some expansion, shall we say. And then the titanium goes, I'm having all of that oxygen, I'm going to attach myself to it, leaving the hydrogen atoms, which then ignite because of the temperature. So you get a bang, bang, steam, hydrogen explosion. So managing the melting of titanium is expensive and potentially quite dangerous. There's a lot of, obviously, process controls in place to avoid that, but it is a concern and something we have to manage. And then with titanium, there's some quite intensive or extensive post-processing required. You may know that when titanium solidifies, it goes through a phase change and leaves something called alpha case on the surface. Now, for the younger contingents at work, when I described that under a microscope as looking like crazy paving, none of the younger people understood what that was, but I'm sure you guys will. And it does look very akin to a crazy paving. And of course, all of those cracks in that alpha case surface are potential crack propagators. So we have to remove all of that alpha case, and that's where the hydrofluoric comes in. So we chemically mill the entire outside of, or any internal features as well, of titanium castings to remove the alpha case. We don't want it on the part. It's like the devil's forehead. You can't machine through it. It's a really, really unpleasant byproduct of the process. And one of the reasons we go into a cold shell is to keep the alpha case thickness to a minimum. So in America, they tend to go into hot shell, which propagates more alpha case, more to remove, but from their perspective, that's just quicker and easier. For us, we like to minimize the alpha case and the grain growth within the material as well. So that's why we go into a cold shell. The other thing we have to do on most parts, particularly if it's going on a plane, it's going to get hot isostatic press. So we need to close up any potential internal voids. We would hope we wouldn't have many anyway, but we would need to try and heal those, which the hipping process does and densifies the material from its as cast form. Now, when I mentioned the large furnace, it really is large. A couple of ne'er-do-wells out of our melting team, they're gazing up into the pouring chamber. If you can't see at the back, there are these little people here. So that furnace, including the ram, is about 18 meters tall and is housed in an extension to our building. And we can just about squeeze 1,250 kilos of molten titanium into the crucible. The crucible sits on this hemispherical door here and goes in and out of the melting chamber on rails. So what basically happens is it's vacuum arc remelting, which starts with an electrode as its starting stop, unlike most of our other materials, which start as scraps and offcuts. So we're starting with an electrode that is 2.2 meters long, 585 millimeters diameter, and it has a stub at the top that the crane can hold on to. That's a 40,000 pound ingot of titanium. And we're going to pick it up using the hydraulic ram at the top and into a vacuum chamber, which is over the top of the melting chamber. In a different process to ISM, what we're going to do is basically bring the positive and negative terminals together using the electrode and the copper crucible. We put a little striker plate in the bottom to protect the copper, and we create an arc, and that arc grows bigger and starts to melt the material off. And that process goes on in the central cylindrical chamber there in the middle. Again, under vacuum, all of this is in vacuum. The door at the bottom shut, and a vacuum is drawn there as well. And at that point, we're using the princely sum of about 28 volts of electricity, but at 40,000 amps. So for those of you good mathematicians, that's about 1.6 megawatts. And we're going to be pulling that for around about 20 minutes to get the melt pool that we need. And then the computer cleverly and simultaneously withdraws the electrode, which has been moving up and down to maintain the gap, but also obviously as the crucible fills up, it needs to retract. It fully retracts, which allows the crucible to tip. It pours the material down through an opening here and into the pouring chamber below. And the turntable that the two guys are stood on is static if we're pouring statically, but it also will spin up to 300 RPM. And the peripheral speed on that bottom turntable, as you can imagine, at 3 meters diameter is significant. We can get up to about 50 G, but we've yet to develop a shell that will stand 50 G. But this gives you an idea of the kind of numbers going on. And those shells could be 230, 240 kilos a side before the metal goes into them. So there's an awful lot of physics at play when we're melting, particularly centrifugally. It's worth just pointing out, it says in the text there that there are probably 4 furnaces in the world over 750 kilo melted plate. One of those is in Belgium, one is in North America. There's probably one in Russia as well, which is very big, but they only melt into graphite molds. So we're in exclusive territory with the bar furnace. So that's where we've been a long time ago, where we were in recent history, and what we're doing at the moment. I guess the next natural question is, what are we doing next? So I'd have to probably review my restrictive covenants to tell you what I'd like to tell you about the MBO. So we maybe do that when it's not being recorded. But let's just say there was a preoccupation with winding the business down and closing it rather than taking an alternative route. And I'm pleased to say that we managed to defy the odds. We saved, at the time, 75 jobs, got 80 staff now. And also, what I believe, a little bit like Forge Masters, which has just been obviously taken into ownership, governmental ownership, we kept a sovereign capability open for the UK defence and aerospace sector. So really, really important. However, that was really the easy bit. Didn't seem so at the time. What we do need to do is obviously keep the business sustainable with rising costs and all of the other things that challenge the businesses all around the world. So the key to our growth is volume, having sufficient volume to be able to make castings profitably, which is not perhaps as simple as it might seem. And part of the reason for that is we're very niche. So I showed you that very pretty impeller, which is probably nicer than you'll get from any other foundry anywhere else in the world. But if it doesn't matter if it's pretty or not, then nobody's going to buy it because it's going to be more expensive than a less pretty one. And that is where our dilemma is that we have to find the customers that are looking for Class A type impellers, those that are going to go into quite often nuclear pumping of cooling water and so on. The specifications for those impellers are amazingly high. They don't lend themselves to traditional casting processes. They do lend themselves to us, but because they're good, they don't wear out very often either. So we're kind of victims of our own success in a sense. So it's that is our single biggest priority at the moment, is growing our business. We could do with another F-35 type contract. So we're doing 40 parts a month on F-35. F-35 is $1 trillion program of Gen 5 fighter aircraft. It's also the fighter aircraft. The parts we make only go on the B variant of that aircraft, which is currently on trial with the RAF Marines on the 2 new aircraft carriers. It's a fascinating aircraft in the way that it operates. Although I have to say, the Harrier have been doing it for quite some time before then, but we don't go there with the Americans. So what I would say is that we could do with finding another contract of that magnitude. If we do that, we're away and running. We need that kind of volume again, and we'll be in a very different position. Then we can sort of gather ourselves and push on to the next level. We estimate, I mean, we're currently, just to put it into context, we're about 6.6 million turnover, and we estimate we can do about 30 just by increasing our workforce numbers. We don't need a massive amount of capital expenditure. We'd hope not to after £30 million worth of investment in equipment. We're continuing to invest. We already have 3-axis machining and some turning capability, but we've just bought a 5-axis machining center. We're trying to vertically integrate our machining as well, because oddly, and bearing in mind, although I am from God's County, I respect that Sheffield and the city region around Sheffield has some of the finest metal production and machining capability of anywhere in the world. Sadly, that doesn't seem to apply to castings. So most machine shops don't like castings. They come in, they're dirty, they're not consistent quite often. I mean, ours are quite consistent, but they don't have datums on them to start with, like a bit of round bar. So before you even open up the conversation, there's a bit of problem with castings. If you then add to that we're going to ask them to carry out some machining work for us, we're probably going to deliver it to them later than we said we would, and then when we do deliver it to them late, we're going to want it back the next day. So as subcontract clients go, we're not really top of most people's lists. But then we get the scrap scenario. So getting something like that impeller to the position of where it needs machining, if someone scraps it, that could be a £20,000, £25,000 mistake. And of course, like all good terms and conditions, you get the next one machine for free, which doesn't really help us that much. We've got a 12 to 16 week lead time to replace the part and an awful lot of cost down the drain. So integrating machining is really key to us. We've also implemented shift patterns. We want to become a 24/7 operation. I have previous experience of introducing 24/7 operation. And what I will say is, just putting the numbers to one side, there's something about having a business that has a constant heartbeat that is difficult to quantify, but I know it works very, very well. You also have, of course, inbuilt disaster planning, disaster management. So you're not relying on a fire alarm going off and the fire brigade attending and putting you a fire out, hopefully not with water if it melted titanium. You really don't want to be reliant on that. If you've got people on site, usually they can tackle it if it's a minor fire, but most importantly, they can raise the alarm, they can take action, evasive action. It also, with us quite often having a lot of nickel-based alloys on site, means chasing off guys in white transit flatbacks as well who are trying to take our scrap skips away. So shifts are key to us and growing the business. The other things we've got to do is, and I hope I haven't upset anyone on the call, but as a reasonable manufacturing engineer, at least in my own mind, there's an innate understanding of what process suits what kind of part. And of course there are overlaps and there are no strict rules, but it's surprising how often we get asked to make castings which just look like a fully machined part. We ask ourselves, why are they coming to us? I'd fully machine that. Machining has come on in the recent history in the same way as castings have. Fabrication, some parts just lend themselves to fabrication. There's very, very often no advantage from making them from a casting. Often what people look at first is, oh, it's about saving the raw material, like in the example I mentioned early in the presentation, where you're taking a huge block of aluminium and machining 90% of it away. Yes, getting near net shape on that has a massive transformational advantage. But what you find with a lot of parts is that you're going to save a lot of material, which is not that expensive to buy. It's the value add that costs. I mean, we pay, just to give you an indication, and I'll use two extremes there. We buy titanium for melting at around about, she's gone up, so about £16.20 a kilo. Our most expensive part sells for £3,250 per kilo. So there's a huge value add proposition there, and that's the same with any process. So people get all caught up with the raw material you're going to save when it's actually probably quite a small amount of the cost. And what happens as well is they forget that you get your casting, you've still got to machine some of the features. We can't cast threads, we can't cast bores to a couple of microns. So you've then got to pick up a casting which has no datums on it often, and you're going to still have to machine it. So again, we've got to try and educate manufacturing engineers to look at process conversion where it's appropriate. So I'll give you a different example where we took a bill of materials of 9 separate aluminium parts that was assembled, fabricated, and partly screwed together to make a flat actuator for a 777 Boeing freight aircraft. We changed that to a one-piece titanium casting. Well, those of you who understand the relative densities of aluminium and titanium will say, well, it must have been heavier. Well, of course, there's always a compromise, and what we actually managed to do was we made it lighter, stiffer, cheaper out of a heavier material, and that was done by using what we tend to call optimized topology. I prefer to call that putting the right material in the right place where you actually need it, not in fresh air. And that's what we did, and that, of course, from a management point of view, when you're building an aircraft, being able to reduce the bill of materials is critical. You don't need any further corrosion proofing or anything on the titanium, whereas you do on the aluminium. There are chemicals involved. So there's a whole host of great benefits from doing that. And yet, normally, the last thing you'd think of to lightweight a component is to make it out of a heavier raw material. So it just goes to show that, and this manufacturing engineering bit is where we're targeting the most of our efforts to try and take, where it's compelling, fully machined, fabricated or forged parts to castings. And it's worth saying, when we do centrifugally cast titanium, the material properties we achieve are the same as or superior to forged properties. But again, we have a complete mindset in design, particularly in aerospace, that forgings are it. That's the pinnacle of material properties, and we would beg to differ. And interestingly, it's Airbus who published that documentation around 10, 15 years ago. And I'm going to say that we want to promote castings versus ALM. We noticed that it's one of those be careful what you wish for things. Very encouraging to hear politicians up and down the country talking about manufacturing. However, what it seems to mean is that they've just got this idea now that we can 3D print everything. And what I will say is, I have a lot of time for ALM, and I think, you know, as an engineer, you've got to admit it's the most elegant way to make pretty much any part and be able to create internal structures that are strong but light and all of those great things. The fact remains is it's a long, long way off. Yeah, and yes, there are 3D printed parts on aircraft. Very few are structural, and in particular in the build axis, it's the material properties tend to lag well behind the established technology. So what we're trying to say to people is, you know, use castings where we've used the good bits of ALM. So we build our pattern using ALM, but we're using. Anybody know how old the investment casting is? As a matter of interest, I would like to ask this one. Yep. Any advance on 2,000 years? And anyone, any more for any more? 6,000 years. So 4,000 BC, copper frog, made by an elementary investment casting process. So what we're doing is a real nice fusion between something that's established. Castings aren't perfect, but we know what their shortfalls are, and then doing a nice fusion between that and modern 3D printing to give something that will keep us going, I believe, for probably the next 15 to 20 years. Even with the accelerated advancement of ALM, there'll still be a room, I think, for castings to play a part, at least I hope, until I retire, which at the going rate is probably going to be about 70. And of course, as a business, we want to leave behind a legacy that allows that business to continue. So rather than being against ALM, we recognise some of its shortfalls. We're able to overcome some of those, but we're also looking to develop complementary technologies, and who knows, we may even embrace ALM ourselves at a future point. So we shall see. So that's all I've got to say. I hope it wasn't death by PowerPoint. Anybody got any questions? Could you all hear me okay, by the way? Yeah. I usually get told my voice is too loud rather than too quiet. Yes, sir.
You use VAR to balance with titanium.
We do for the large furnace.
Why don't you do it? Is there something unique about titanium?
No, so it is in effect a very, very similar process. So the VIM part of the process is done for the single, double and triple remelting of the electrode. So the electrode as it comes into us is produced by the VIM process. But for production of castings, the VAR process is superior for what we need. Interestingly, our other process is ISM, where we still have a copper crucible, but that is filled a bit Jenga style with lots of offcuts, and we melt that just using an induction coil. So that we do ISM and VAR, they're the two technologies we use. But our ISM furnaces are much smaller. But when we buy an electrode in, that has been VIM melted, usually triple VIM melted.
You mentioned the coarse-grained surface structure.
Yes.
What can you say about the horizontal microscope and macroscope?
Good grief, I have no idea is the honest answer to that. I did say I'm not a metallurgist. What I will say is that, on what I understand, is what we're looking for actually is to constrain that grain growth. So in actual fact, using the cold shell technology and introducing argon immediately after the pour is complete, we want to get that titanium, once it's filled the void, including the fine detail, we want to get it cool as quickly as possible so the grains don't grow. We're looking for a very, very close, small grain structure in titanium.
Does your passing process offer an advantage convention in terms of underground or the microstructure and
From
grain flow. It just seems to me that it's a very interesting area. Further,
yes, so versus a hot shell, where the titanium takes longer to cool down, an awful lot longer in some cases, then you get an increased grain growth during that phase, and that's what we want to try and avoid. So that's the extent of my cold shell titanium casting knowledge. I'm sorry if that doesn't quite answer your question, but what we do see is that our properties are demonstrably better than castings produced using the hot shell process in mechanical properties terms. And in particular, the key thing for aerospace users when it comes to titanium castings is the fracture toughness, because that's where you struggle against forgings. And our fracture toughness levels are extremely good in comparison to forgings. I mean, it is interesting. I've seen some forgings, particularly on the Eurofighter. So they've sold that, well, recently sold another batch of, I think, 75 Eurofighters, and we do a couple of parts for that. But we got dragged up to Salisbury to look at the Eurofighter, and they said, we've got to take cost out. Basically, they've sold them below the requisite margin. And the reality is, it's a legacy aircraft that nobody wants to put a lot of resource into. But they were making a forging that holds the vertical stabilizer fin on to the fuselage. And it was crying out to be a near net shape. And they make it out of a forging because everyone thinks forgings are great. And it's a lump of titanium. And then they machine most of it away. So any grain flow that they did have has been quite severely cut. And then they weld it to another piece of titanium and create an awful lot of porosity because they haven't got the welding process right. And I said I could produce that from a titanium casting for you with 1 millimeter machining all over. Job done. Well, we'll never get that process changed through, you know, and you begin to wonder why you bothered going all the way up to sunny Salisbury, but there we go. That's reticence to change, I guess. Yes, sir. Well, we don't produce, we cast. So we buy in and cast, but it's 6.4 without any shadow of a doubt. It's probably, of the titanium we do, it'll be 85% 6.4. We do a little bit of CP or commercially pure, and even less 553 is the other grade that we do use from time to time. And the big winner potentially is titanium aluminide. That's the material that we've done some development work on, but it's incredibly difficult to cast, but has a whole host of more advantages over and above titanium for a high temperature use.
One question online, which is sort of related to the titanium casting process, melting for us. When you melt VAR melting the titanium electrodes, what is it melted into to keep it molten before you actually then tip it into the mold?
So it's into a copper crucible, and the continual arc keeps the material at temperature. So there's an awful, as you can imagine, at 40,000 amps, there's an awful lot of power going into that mold and into the crucible and the electrode. But what we do is to create homogeneity in the mix itself and to keep the temperature uniform, we have an electrical coil that's not an induction coil as such in melting terms, but it does create a stirring process. And it's actually problematic because if you get 1.2 tons of molten titanium moving, it has quite some momentum. And then when you pour it, it tends to go up, left, right, and down, anywhere but down the hole you want it to go down. And we end up scraping off the inside of the furnace. So we have an electrical switch which reverses that, but you can't stop the rotation quickly enough. You have to get it down the tube because it's going to start solidifying. And that affects our skull weight, which is crucial to the commercials of titanium melting, but also trying to get it out of the crucible once everything's solidified.
Any more questions from the floor? No? Well, before I start, thanks, Richard. I'm just going to stop the Zoom presentation.